Oh, hey, didn't see you there. Welcome back to A View from Earth, brought to you by the Fiske Planetarium at CU Boulder. We hope you're all doing well and staying safe. As with the rest of the university and many public spaces around the world, Fiske's Theater is closed to the public for the foreseeable future due to the COVID-19 epidemic. However, we are still so committed and excited to bring astronomy and education to you that we started a whole host of free online offerings so that we can stay connected and keep bringing you the Fiske content that you know and love. Plus, some new stuff like this podcast. So thanks for tuning in and learning with us here today. My name is Colin Sinclair. I'm an undergrad at CU. I study astronomy, and I'm also a presenter at Fiske when the building is open. Otherwise, I co-host this podcast. With me here is Tara. Hi, Tara.
Hi, Colin. I'm Tara. I'm a planetary scientist and a CU alum. I'm also a presenter at Fiske when that's an option, and I'm the coordinator for our outreach program.
Thanks, Tara. So today we're going to be talking about something called citizen science, which is when scientists involve people that don't have formal scientific educations in their research. And one of those things that we'll kind of get into a bit is called recon. And I'll let Dr. John Michael Keller, one of our guests, tell you about recon. The other project is called Planet 4, which will be presented to us today by Drs. Michael Anya and Anya Portyankina in their journey learning how to set up and run a citizen science project. I think you're really going to like it. But first, the news.
And bringing us the news today is our friend Joe. Welcome back, Joe. How are you?
Doing well. How are you, Tara?
Doing good. What have you got for us today?
Well, as Tara said, I'm Joe Zader. I'm a presenter at Fiske, studying at CU. And for the news today, I got some fresh news for you about today's topic of citizen science. More specifically, citizen science is focused on exoplanet discovery. So you probably know at this point that we found thousands and thousands of planets outside of our own solar system. More than 4,000 have been confirmed since astronomers first found one in 1995. These were found, several different ways, methods of detection like radial velocity, which, the wobble method, as we like to say, or by studying light curves for the transiting exoplanets. Some have even been by direct imaging, which is, just amazing. I mean, how cool is that you can actually see another planet orbiting a different star than our sun? Anyway, no matter which of those methods were used for those 4,000 or so exoplanets, what is it that they all had in common? Well, they were found by professional astronomers and scientists. All those until now, of course. So recently, exoplanet discovered this year, made public just a couple of weeks ago, was found by an amateur astronomer just hanging out in his backyard. This exoplanet has been dubbed Gliese 3470c, and it's shaping up to be a Saturn-sized body, likely to reside in the star's habitable zone. Completes an orbit every 66 days, so fairly short year compared to ours at least. And it's around an M dwarf star or a red dwarf star that's about half the mass and half the overall size of our star, the sun. It's about 100 light years away, and you could actually look up in the sky, and in the constellation Cancer, you'd find its location. Note that professional astronomers still do need to confirm the existence of these exoplanets through various other means, but the data right now is looking quite good. It's pretty cool. So how did this guy do it? Well, his name is Philip Scott. He's a retired teacher living in Oklahoma. And while ultimately he's the one that aimed his 12.5-inch Newtonian telescope to watch this star's light dip periodically when the planet would pass in between the star and his telescope, he actually credits the network of amateur astronomers that he works with. Specifically, it's a group called the Habitable Exoplanet Hunting Project, or HEHP, because everything needs a nice acronym, of course. The group was actually formed through a YouTube channel called the Exoplanets Channel. There's folks from more than 10 different countries across 5 different continents. They're participating in this project. They track a number of stars that are all within about 100 light years of Earth. And we know that these stars, we already know these stars do have exoplanets. They're just looking for additional exoplanets. And specifically, they're looking for habitable zone planets using the transit method that I kind of talked about before. They sort of use this transit method to tease out the data about additional planets that could be around stars like this one that they found. Really, it's really showing the power and usefulness of citizen science. Even in fields that most people think require massive and expensive equipment, teams of scientists, that sort of thing. But this is a great example of how really anyone that's interested in the world and in the cosmos around them can find a way to contribute to science and to astronomy like this, just like Mr. Scott and his team of amateur astronomers did in their backyards. Now, what I'll leave you with then is, I think, a pretty kind of a neat part of this story. When he retired, Mr. Scott's students had asked him what he was going to do now that he's had all this extra time. And he told them, quote, "I'd like to discover a new planet." That might have seemed a little bit like a joke at the time to some of the students, but turned out that's exactly what he did next. So everyone else, get out there and keep on looking up. You never know what you might find.
That's
Nice.
so cool. Good for him.
Yeah, that's a great story. That's awesome.
I couldn't believe it. Just sitting out there in the backyard, he talked about how he goes and just looks at stars with his wife all the time, and it's a good way to spend retirement and find a planet.
Yeah, absolutely. So you said that Mr. Scott had used a 12.5-inch Newtonian telescope, which, by the way, to anyone listening, for me as a person that does not own a 1.5-inch diameter telescope, is a very large telescope. So it's backyard, but it's still really big. But then later you also mentioned that his group was parsing data, was looking through data that already existed. Am I understanding that right? So it looks like they're both looking for they're gathering new info, with their telescopes, but also looking through data that has already been, gathered and created maybe through past missions or other people or something like that.
Yeah, exactly. That's spot on. And good point about the telescope. It is a backyard telescope, and he did name it I forget the name he had it, but it's actually named an observatory. But these pictures of it is just in his backyard. So granted, yeah, it is much bigger than most people I think would have, but it is doable. And I saw pictures. Kind of neat. But to speak to that about the new data versus the old data, that's right. To my knowledge, they are using some of the old data too, because I think they were looking at it and said that there were certain anomalies in the light curves that showed that they could be several other planets, but they didn't have enough data of actually looking for the transits, because those really super big, professional, expensive ones, they can't always have it trained on one single star for a year or something like that, like this guy did. So they're kind of looking through old data for clues of what they might want to look at, and then using that to kind of constrain how they're looking and where they're looking, and trying to find new patterns. And so far, it seems to be working, at least for these guys.
Well, Joe, thanks so much for giving us the news again today. It's always a pleasure to hear from you, and it's kind of a nice inspirational one, a nice one to end on, I think, for season 1. So that was a lot of fun.
Oh, well, thank you. It's been a real pleasure as always.
So now we are joined by Dr. John Keller, the director of the Fiske Planetarium. John, thanks for being with us.
It's a pleasure to be here.
Really quick, would you briefly explain your backstory and how you ended up doing what you were doing? What brought you to being the director of the planetarium and other things that you do here at CU Boulder?
Oy vey. Sure. So I went to my first planetarium show as a second grader at Capitol High School in Boise, Idaho. I distinctly remember that visit with the Clayton family and the Keller family. And that's when I first said, whoa, stars are pretty cool. We'd moved from Los Angeles to Idaho right before then. And so I had the benefit of spending the rest of my childhood through high school growing up in Idaho, which has very dark skies. My parents got me a telescope when I was a sixth grader, kind of 4 years later. And I essentially knew from all through my high school years, grade school through high school years, that I really liked astronomy. When I went to college, I did not pursue that. I actually studied biology. And I didn't really know why I was studying biology, except that I liked science, and biology let me take some physics and take some chemistry and take some biology and take some astronomy and take some earth science. And so I generally had the opportunity to take lots of science classes, but I wasn't really focused around where I wanted to go with that degree. And so after I got to junior year and declared my major as a biologist, I said, well, what am I going to do? And I was presented with the opportunity to stay at Stanford for one more year and get a teaching credential and become a high school science teacher, which actually was perfect because I realized that I really liked science, and getting to explain science, work with students about science was really, really fulfilling. During that time that I was teaching high school in the Bay Area, after I graduated, I also had the chance to work at NASA for several summers aboard working with the Kuiper Airborne Observatory, which is an airplane that flies at about 40,000 feet to look at the infrared universe. And so I did summer work at NASA Ames Research Center, and I did school year work during the school year teaching high school students. And it was really through those 5 years of teaching and researching and teaching and researching that I realized that I did want to be an astronomer. I just hadn't realized that till I was 26. And so I actually then came to the University of Colorado Boulder to get a graduate degree in astronomy. I didn't have enough physics and math as my classmates. And so I actually took a lot of undergraduate physics classes that I hadn't had yet as a biologist. And I ended up finishing with a master's degree from CU Boulder, but it was actually an enrichment in my physics and math background. And then I ultimately finished my PhD in planetary science at the University of Arizona, where I studied planetary science and Mars, but I also did astronomy education research. And so I think in doing that, in that transition from high school teaching to eventually becoming a professor, I realized that I liked doing astronomy, but I still liked teaching astronomy. And so I mostly did astronomy education research in grad school, at Cal Poly, where I was for 10 years, and then here at CU Boulder, where I've been for 2.5 years now. When I was in my graduate program at Arizona, I'd worked at Fiske when I was here as a graduate student. And I had realized that I would always like to have been a professional employee at Fiske. But at the time that I was in grad school, I was not able to be here yet. And so when I saw that Doug Duncan was retiring after being here for 15 years, I was really excited about the opportunity of being able to return to the planetarium. That's probably a much longer-winded answer than you wanted, but that's my backstory.
No, that's perfect. That's exactly what I was looking for.
So you're working on a project called RECON. It's sort of like a citizen science-y observation of Kuiper Belt objects and stuff. Can you give us a little bit of a broad overview of kind of what RECON is?
Yeah, certainly. So I was really fortunate to have met a colleague named Mark Bowie from the Southwest Research Institute, which is here in Boulder, Colorado as well, back in 2010. At that time, Mark, who's one of the, he's been studying Pluto for the last 35 years of his life. So he's one of the renowned astronomers who knows about the outer solar system. He approached me with an idea of creating a network of telescopes that would stretch across the entire Western United States that would be capable of measuring objects in the outer solar system using 11-inch telescopes. And so, and he even at that time in 2010, he had said, I want to do this with high school students. I want high school students to help me do the science that we want to do with the outer solar system. And so that's what RECON is. It's a network of 60 communities that stretches from Yuma, Arizona, right on it's the southern border of the United States, up through the Colorado River, the backside of the Sierra Nevadas, up the backside of the Cascades, all the way up into British Columbia. We go have telescopes, 6 telescopes, 7 telescopes north of the border into British Columbia. And those 60 telescope sites are run by high school students, high school teachers, and community members, over 250 of them in those communities. The science we're trying to do is that these objects in the outer solar system called trans-Neptunian objects are out past Neptune, they have orbits that bring them in and out of the orbit of Neptune. And when objects in our solar system pass in front of stars, if that's a star, you see that's a star, and an object passes in front of that star, the object will make that star blink off and blink back on. It'll basically block the star for a certain amount of time. That's called an occultation. Occultation comes from the word occult, which means to hide. And so when an occultation occurs, the star is being hidden by the object that's doing the occulting. if you can catch that measurement of the star getting blocked, you can actually figure out the size and shape and dimensions and rings and moons and other features of the object in our solar system. And that's what we're doing with recon, is studying these are known Kuiper objects and trans-Neptunian objects, and we're figuring out what their properties are using this technique.
That's very cool. And you said there were more than 250 people that are working on this with you?
Yeah, so there's 60 communities. Each community has at least 2 people, and some of them have 20 people involved. And so, you know, over the course of the 5 or 7 years that we've had the project running, we've interacted with well over 250 individuals. Any given event, we've only had one event in the 7 years where where it was clear skies across the entire network. I mean, this is a 2,000 kilometer network, so there's always going to be some storm front going over mostly Oregon and Washington. They have the worst luck, obviously, but there's always some fraction of those that are clouded out and not able to observe. But we've always had a certain number of telescopes, you know, actually comparably, there was also one night where all 60 telescopes were completely clouded out. I don't know if you remember the Snowzilla. It was the Snowzilla storm of 2014 or 15, which caused a huge blizzard in the East Coast. And 4 days before that, that storm system was marching over all of Recon. And we had no telescopes that were able to collect data that night. Occultations are tricky because it's not like studying a galaxy where you can point your telescope at the galaxy anytime it's clear and then like wait a couple more nights for the next night it's clear. It's actually a very precise time, like at 8:47 a.m. Sorry, 12:47 a.m. on a Thursday night that the occultation is actually occurring. And so if it happens to be cloudy or if your telescope isn't hooked up properly at that moment, then you can't actually collect data for that event. It's been a really great opportunity to work with great, amazing teachers, amazing students, wonderful community members. We really can't do this science without their help. Like I can't be in 50 places at once and so it's been a really great way to engage students in the rural communities that we're working with to help us study our solar system.
Yeah, that's very cool. And aside from like weather challenges, have you found any other like really difficult things about working with that many people?
I mean, it's not simple. I think the biggest challenge that people have faced is that I would say 1 out of every 5 of our team members had ever used a telescope before becoming part of this project. And so that's both a challenge and a success. Challenge because we clearly need to train and provide support and help people get up to speed with how to collect the measurements we're working on. Success from the sense like those communities that have become successful has been really have gained amazing skills. And the other success is every team has come to realize just how complicated science is. Like science is not just reading something out of a textbook and saying that the solar system has this many planets. It's a process by which you have to really get out there and get your feet wet, or you get your cold. You get cold if you're in the mountains in 20-degree weather to get the data that you need to collect. So there have been clearly times when people haven't gotten on the field at the right time to collect the data that we had hoped they could get. But in each of those experiences, they've also learned to become a better observer the next time around. I think the biggest systemic challenge, and this is kind of a broader issue for the United States in general, is that there is a significant teacher turnover rate, right? So we typically have lost roughly 10% or 10 to 12% of our teachers every year to either going to other districts that don't have our telescopes or to going to other professions. And that's just kind of the nature of teaching. Unfortunately, is that there is a fair amount of flux of individuals staying at one school for the 5 to 7 years we've worked on this project. It's no fault of the teachers, it's just the reality of the situation. And so we've had to retrain each of those communities where we've lost that main teacher, who's really, the teacher is the glue that determines how much students get involved or don't get involved or how active the teams are.
Yeah. And I think a lot of people get surprised that you're doing this whole big sort of project with these people that are definitely not professionals at this. They're brand new at getting into telescopes and science, and you're doing it with a pretty basic off-the-shelf telescope. This isn't some big 24-inch thing like we have up at the observatory.
Mm-hmm.
I think, are they like shocked when you say, yeah, we're just doing this with a little 11-inch backyard telescope, but we're doing all this really cool science with it?
Well, that was why I was so excited about the project when I first heard about it. And I apologize for the siren noises outside. There's a fire truck going by. Yeah, the reality is that these objects, I was teaching high school when the first trans-Neptunian object was discovered. And I never dreamed in my life in 1992 that I could use a telescope to learn something about that. I just assumed that it was something that happened up on top of big mountains. The reason this works is that we don't actually have to see the objects that we're studying, because those are actually super, super faint, but we have to be able to see the star. And so as long as you have a bright enough star that's being occulted that you can see with an 11-inch telescope, then you can do the science we're talking about. And so it's the fact that there are bright stars that you can see with these small telescopes that lets us do this technique. It's not the only example of how you can use small telescopes to do science, but it's definitely one of them. And so there's a range of investigations you can do. There are certain things you clearly can't do with an 11-inch telescope, and we're not trying to do those. But this is a really good application of that size of a telescope. And then the students and the high school teachers and middle school teachers and community members who have been part of this project, I guess that's just another thing I wanted to put a huge shout out to them. They've been phenomenal in just like, it's a big ask to say, I want you to use something you've never used before to measure something that's this far away with an object that's far away, that's dim. And there's tons of learning that's happened, but they've been really stellar, participants of just getting in there and getting their feet wet and doing your best, because that's all that you can do, right? You just give everything your best shot and you learn from every experience that you have.
Yeah, and you guys were actually able to use this sort of occultation technique in the Recon Network to support the New Horizons mission in their observations of that new object, Erika. Mm-hmm. Like, was that super exciting for these kids to be involved in like a huge NASA mission?
So for Erika, which was the second target of New Horizons after Pluto, we did not have any students who officially helped with that campaign, but we did have about a half a dozen or more teachers who are part of the Recon Network who we deployed to Africa and South America to participate. You actually had to be in the Southern Hemisphere to measure Erika. And so those half a dozen Recon teachers were huge contributors. It was part of these were epic 60 and 80 person teams that did the science, and they were parts of those teams. There's a new mission that's coming, that's going to launch this decade, that is another outer solar system studier. It's called the Lucy mission, and it's specifically going to study the Trojan asteroid belt, which are the Trojan asteroids are asteroids that are trapped in front of and behind Jupiter in their orbits around the sun. They're all about the same distance as Jupiter from the sun. And due to the gravitational interaction of Jupiter to the sun, they sit in these places that are stable places for asteroids. And Lucy is going to actually fly by 5 of those Trojans. We actually had Recon contributed. The paper just got submitted last week. We had a team of Recon specific people in Northern California and Southern Oregon who deployed a very special deployed group of 8 telescopes to measure one of those objects, the Lucas Trojan asteroid. And so they made a measurement that's 1/5 of the publication. We did 5 of these occultations, and the Recon team members were part of that one. And we're going to do more of those. We're doing another Lucy mission in September coming up of an asteroid called Euripides. And so more and more of these deployable campaigns of targeted asteroids that NASA's flying missions to is awesome.
Very cool. Well, Dr. John Keller, thanks so much for joining us today on the Fiske Planetarium podcast, soon to be officially named. It has been such a pleasure to talk with you and learn so much about what it is that you're doing, and make everyone excited about what's coming up in the future for the planetarium.
Yeah, and thanks to you, Tara and Colin and John, for putting this together. I mean, I know that you've thought about this and wanted to do it for a number of months, and silver lining, we are finally now initiating what hopefully is going to be a lasting thing that you will tell people 10 years from now. I started the podcast. It's like I wrote Kids in Space.
That's right. Yeah. Yeah, well, we're really looking forward to see where this goes. So it'll be a really good time. Awesome.
Thanks for joining us.
You're welcome. Thanks so much.
So now we are talking with Doctors Michael Anya and Anya Portyankina, who run a citizen science project looking at the surface of Mars. People who participate in this project can help find and analyze jets of material that spray up from the ground, and it helps them understand wind patterns in different locations around the planet. Dr. Portyankina brings an expertise of ices in the solar system, studying those with data from spacecraft and from experimental labs around the world. And Dr. Anya creates new and innovative ways of analyzing data using a variety of programming languages and works with instruments studying Mars, the Moon, and Saturn's rings. So thank you guys so much for joining us today.
Thank you for having us.
Introduction.
Yeah.
Thanks.
So I just wanted to start off real quick and get a little bit of information about you guys. So aside from the citizen science project, what are your sort of main fields of study? What is it that you like working on?
Yeah, so as you said, I am interested in everything I see in solar system. So all the surfaces that have ice, Martian polar regions are my first and prime interest, but I'm also doing some of the outer icy satellites. So the satellites of Saturn, a little bit Europa, a little bit of Moon as well, also on the surface. Yeah, but my main interest is seasonal activity in the Martian polar regions. So everything that relates to ice and atmospheric interactions over there.
All right, yeah, and my main interest actually, I think over the years has me more pointing towards data analysis, meaning the power of really good math applications on multidimensional data sets and correlations between different data sets. But I'm also very interested in creating new instruments and making these measurements the best they can be. So I'm involved a little bit with the calibration, or maybe actually more than a little bit, involved with the calibration of the Lunar Reconnaissance Orbiter thermal radiometer. This is where we try to measure the coldest temperatures, well, also the hottest, but I'm fascinated by the coldest because there is less photons per second. So it's kind of a signal to noise problem. And you have to be very careful with what you know about the instrument to understand how cold it really is on the moon. And yeah, the other data analysis task that I really like is the complexity of the Saturn rings, because it has so many patterns that I always describe as some kind of visualization of math, or the complexity of math, because we think that these structures occur due to interactions between the ring particles and the moons in really complicated math resonance interactions. And they are totally different depending on where in the radius in the Saturn rings you look. And I'm trying to come up with image analysis routines that kind of quantify these structural differences per ring radius, so that we can maybe come up with equations that describe better why these sharp boundaries, for example, exist in the C ring, or why the clumpiness is different in different areas of the Saturn rings. But just one last thing, where the things are combined is my work started as looking over the shoulder of Anya with her work on the South Polar area of Mars. And there I also focused on the data to make it basically more, make us more capable in analyzing more data in a faster time by doing parallel map projections routines for this huge gigabyte size high-res images.
Cool. So let's talk a bit about the citizen science project that you two are working on with the fans and jets on Mars. Can you tell us, just kind of like intro us onto this project, how it started and kind of what it is?
So sure. So the jets on Mars, not many people actually know that we have something like geysers erupting in the southern polar regions, well, actually in both polar regions, but we focusing here with this project on the south. So let's start from the background. Every year on Mars, in polar regions, CO2 deposits as an ice layer. So similar to how snow falls in our winter in high latitudes, but on Mars it's CO2. CO2, or what we usually know here as a dry ice, something that you use to cool your drinks maybe. So that ice is a little specific, and particularly because on Mars, the conditions are such that it can either exist as ice or gas. So as a gas, it contributes to the atmosphere. 95 plus % of Martian atmosphere is CO2. And as the ice, it deposits in winter hemisphere on the surface. So then what happens actually in early spring after polar night, again, similar to Earth, where in high latitudes on Earth, you have polar night for several months, there is no sun at all. And then in spring, the sun comes up. And what's fun part about CO2, that it's actually transparent for visible radiation and opaque for thermal radiation. Analog might be the greenhouse effect that is talked a lot recently for Earth's atmosphere, because it warms up as it creates climate change. So on Mars, it happens with CO2 on slightly kind of smaller scale. Sun energy penetrates through the layer of CO2 and hits the bottom, where it can actually warm up the surface of Mars itself, which is now covered by the CO2 layer. And it rises temperature, and CO2 starts to sublime. It builds up pressure for a bit until the ice cannot hold it anymore. The ice breaks, and that gas rushes out, and that's what creates kind of a geyser structure. So we call them jets because Earth geologists insist that the geyser is something related to water in the cavity, and there is no water. It's not involved in that on Mars. It's really the cold gas, and that's why we call them jets. And then atmospheric people complain that the jets is something different, but anyway, so that's the different part. Yeah, so these jets, they bring up some of the material from underneath. They just pick up stuff on the way, and they deposit it then on top of that layer that they just broke through. So what we see when we observe those areas in early spring is that these deposits appear everywhere. And then when time goes by and the CO2 sublimes away completely, it becomes warm and
really quick, just to be clear, when you say sublime, what do you mean by that? When you say the CO2 sublimes, what is that?
Thank you. Sublimes is because, as I mentioned, CO2 cannot be can be only as ice or a gas. So when you warm it up, it directly goes into gas. So it doesn't.
Perfect. So it's ice melting into gas, so to speak, skipping the liquid phase altogether.
Yes.
Okay.
So it's we don't call it melting.
Right.
The correct term is then sublime.
Sure.
You see here in Colorado, sometimes water does that. It gets warmed up, and it actually doesn't melt. The snow gets warmed up, and it doesn't melt. It directly goes into vapor, and it disappears on the hot spring day after snowfall. That's very often what happens. Yeah, so where was I? On the observation, I think.
So once in the spring, once the deposits start to sublimate into the gas.
Yeah, so when that happens, then these fans that we see very nicely in first as a contrast between like bright ice and deposits that was put there that are having some dirt and dust and regolith brought up. And yeah, so they slowly vanish because the contrast between ice and this dark material vanishes. So that's what we observe with remote sensing techniques on Mars. Started from mock or Mars orbiter camera. But so the mock was on Mars Global Surveyor, and the mock team was first who noticed those things, but they didn't have observations enough to say that these fans are seasonal, so they saw the permanent features. And then we got high-res camera, high resolution imaging science experiment on Mars Reconnaissance Orbiter. And now with the better data rates and also more focused on observing actually these features, we see that these fans come and go every year. So they appear every year in spring, they disappear towards summer, and in next spring they come out again. They're different at slightly different locations, differently maybe oriented a bit, but repeatedly over now 7 Martian years, we observe them. So this is a long introduction as a background to story of what we are doing at Planet 4.
So the idea is that these jets, they come out and their direction is controlled by wind when they are blown in the sky into the atmosphere. But the other information is the resolution of the high-res camera is so large that the images are 1 gigabyte size, and they can be up to 20 by 100,000 pixels large. One image only. So to make a precise catalog of all these things and which direction they are deposited was just a too large task. And that's how we had the idea, why not let citizen science help us there? So I don't know if we're already bridging into maybe your next question is like, how did it all get started? But that's basically was the scenario. The high-res data is just too large and we needed the help of citizen science.
Yeah, we did start with some students, got them a task to, count these fans on this location, but then it's just too boring task. There are too many, so we didn't really want to bore our students to death with that. So when opportunity presented itself in form of one of our other colleagues that did this with us, Meg Schlomb, when she basically came up and said, guys, can you do something about Mars for citizen science? We were like, yes, sure.
That's super cool.
Yeah.
So what sort of tasks are these people doing? Are they just identifying the jets? Are they taking more information? And how much sort of pre-knowledge do they have to have coming into this? Do they need any sort of education before just jumping in on this?
No, not at all. We actually have a tutorial where it's shown to you what kind of things, how they look like. And then our major we have different graphical tools on this website. And the major ones are the fan and the blotch. And I don't know if, I forgot if Anya mentioned that already, but if there's no fan during the eruption, then there's no designated direction of these deposits. So then they look like blotchy, elliptic or circular.
Yeah,
so
they
for
just
that,
fall out like a fountain around.
Yeah, imagine it's being spit up and then falls down like a cloud. So, and then has no significant direction, and that we call a blotch. And that is also information for us, because that means that at that time of the eruption, there was no clear wind direction. Either was the wind too weak or was too chaotic. No, most likely we think it was not weak. So chaotic wind direction, that's another topic actually for science analysis we might want to speak later about. But yeah, blotches are no winds and fans are winds. So, and these tools are being introduced in the tutorial, how you place first the marker and how you drag the thing, and then you correct it, shift it, and rotate the symbol that you have drawn on your monitor. And that's it. You do that for all objects that you can identify per tile. What we should mention is all these gigantic high-res images, they are cut into smaller tiles so that they fit nicely on a laptop screen or Windows screen of your standard monitor, so that you can focus. Oh yeah, so that you can focus on the small tile. And that obviously no single person is overwhelmed by a gigantic task of having 100,000 pixels to do. So actually each pixel, it's roughly 860 pi by 600, something like that, pixels to do. And there might be, and even this small thing, you know, if you're unlucky, there might be over 100 fans in there and you have to all mark them. And that's a painful task, and we're very thankful to all the citizens who are going through that effort. But it gives us, for this small tile, the wind directions, and that's really cool. And we can then go zoom out again for the high-res image and have different areas in the high-res images will actually have different wind directions caused by the topography, the different undulations of the inclinations of the Martian surface. They will create different wind directions, and we can see these if we have CO2 jets erupting there. I mean, one side question of our science always is why actually a certain area has jets erupting and the other one not. We're not really sure if we can answer this with a citizen science project, because that's actually focusing more on making use out of the existing ones. But we have actually other parallel projects that map fields where at all we have spiders and fans erupting at all. These are the sister projects that we developed afterwards, which is called Planet for Terrains and Planet for Ridges. That's another use case where more geology-oriented scientists from JPL, Laura Kerber, is using the same kind of mapping tools, but not with high-res data, but with CDX data, a little bit lower resolution, and looking at other features. So the idea of really doing Martian surface-based analysis with good quality images and using citizen science for that really paid out. And it's depending on the amount of detail you're asking for, if that's a faster task to do or a slower one. A funny anecdote, for example, is that the sister project that was created later overtook me in the analysis pipeline and published earlier because their task was not in the detail, but it was just marking if a certain kind of topographical feature is visible in the tile or not. So the scientists were able to go very fast through. They only had to decide between 5 and 6 things. And these were basically 5 or 6 flags in the data at the end. So much easier to analyze as well, while I had to go in and make geometrical averages of all the objects. Yes.
Let's backpedal a little bit, because I think we missed to say that when citizen scientists mark the fan deposits or the blotch deposits, we record all the geometric information about those markings. Mm-hmm. So they have the size, they have the orientation, they have the position in the image. And imagine that everybody does it, and every time is slightly different. So we have 30 markings of the same object, and we have to combine them into one. Because that's what exactly happens, the wisdom of the crowd. The average object of all those markings will be what we actually see. And Michael wrote the pipeline that does that, what we call it clustering. So it takes all this many markings with all those detailed informations, and it cleans it up and removes some people that decided to have fun and draw something different than the fans. That's all happens automatically, and that was a big task that Michael had taken and did actually. And yeah, and at the end we have wisdom of the crowd markings for all our fans over the image, and blotches. So that and that kind of separated. And then we create catalogs of them. So list all of them, list their sizes, their locations, their directions, and that is the data that then I am actually working with. So doing a statistical analysis of them, like currently we are finishing up the paper where we are comparing them with the models of atmospheric dynamics on Mars. So how wind behaves from people who actually can model that, like you know, our prediction of the weather, similar thing on Mars. And it's a tough task because we have very few information about it. But yeah, we are trying to correlate how well they are doing, for example. So there is a lot of steps between actually creating the project, getting the information from people who mark and help us, and then doing science. So there is, each of these tasks is a bunch of subtasks, and yeah, we sometimes getting lost in them as well.
Sure. So, well, to go back just as a tad, you mentioned that sometimes people, for whatever reason, think it's funny to report information that's not accurate, right? So they draw some other thing on this image or whatever. That's one example, and it sounds like you've kind of found a way to flush those instances out. But what other drawbacks are there to having citizens do this kind of science? Are there things that you have to watch out for or kind of plan ahead for when you're having these people that don't have a formal science education do the science with you guys?
Of course there are, and we always say we were very naive when we came into this project at the beginning. We were very excited and thought that it's all very easy, and it took us, I don't know, 3-4 times longer than we first actually thought it would take. So you have to be a little bit psychologist in doing these kind of things. Luckily, we were not the first. So Galaxy Zoo was the first project on this platform. And then there were Planet Hunters as well. So people already collected some kind of information about how you do this most efficient. And it's interesting. It was interesting to me that sometimes I would say basically the wrong thing to do. I remember how we first thought, why don't we give people some kind of virtual prizes, like a medal of marking a lot of things and so on. And we were like stopped by the person who already went through that and said, that messes up everything. Some people really want to earn these badges, and they just do not very good job. They try to rush through their markings. They, I don't know, try to fiddle with it. So don't do that. That was one example. Yeah, with the people who kind of having fun around, they don't bother as much, because this wisdom of the crowd, if you are really doing something absolutely crazy nobody else has repeated, that will not be counted. Michael's pipeline will just throw that away. I think the biggest lesson that we learned, that we actually went very ambitious. Our whole process with markings and having 2 different objects and having them placed randomly in the image, it's complex. And it was complex for us to analyze, not so much for people to mark, but for us to analyze. That took a long time. So now when we are trying to make new projects, like what Michael mentioned, the terrains and so on, we're trying to simplify it. Sorry. The simpler you go, the easier your life will be afterwards. So that's definitely the big lesson for us. But I also think that being so ambitious, we are also very special. There is probably no other project that does this much of post-production on the data.
Well, I think part of what you said crystallizes in the following trade-off that people should think about when they make this kind of project idea, which is the complexity of the analysis setup and the pipeline afterwards, compared to the effort of doing it without citizen science, right? So if your data is large and a lot, so specifically if you have a lot of data, that points towards citizen science. So then, like Anya said, if you can make the task simple, that also points to citizen science. However, if your question on the data is very complex and it needs to be answered with graphical tools like we did on Planet 4, where people need to draw a complex shape, the more complex things are done as a measurement by the citizen science, the more complex your whole analysis pipeline will be. And it it's exponentially growing in time to make that clean and understanding the errors that can happen. The more complex task the scientists are doing this so. So the problem is totally not the ability of citizen science to draw complex shape. Really the complexity is I'm having 30 people or 10 or 15 people doing that. And what do I do with these measurements? I have these complex shapes now. How do I combine them? It's like there are no simple polygon merging tools that know what they're doing. I mean, this is really a problem-specific task on how you merge differently drawn polygons for whatever reason, because some person thought the contrast ends here, the object ends here, or it starts there, or it's in general, it was a low contrast image, and it's just very hard to decipher where the object starts and where it ends. So all these are these error statements that we're fighting with in our Planet 4 analysis pipeline. So like Anya said, if you have a lot of data and you can boil down the question to something like, hey, I have a hypothesis of 5 different things that might be visible in this image. I don't know what. Can you click which of the things you see? And that will be maybe introduced in a tutorial. You know, these things look like that. Do you see this in this image? And our visual cortex of human beings is just so cool in pattern recognition, still much faster without training even. Actually, we are being trained all over the life. That's why our cortex works so well. But to make this task, it's just so much faster than machine learning, where you still need to tell the machine, what does it mean to see things? And what are these patterns? And now go and analyze them, right? So it's just really a fascinating approach of mixture. And I don't see any real negatives apart from this work trade-off that you need to do. How much time and money you have, how much workforce, and how complex is your question that you want to ask the data.
What are there other examples of surprises that have occurred, you know, while you're doing this project? Are there other things that come up where you're like, wow, interesting, we didn't think about that, or, you know, other things that were just kind of unexpected when you work on this?
I think, Anya, some of your statistical results, I mean, one example I can do before you start maybe, but I think you had some interesting statistical stuff. I mean, for the wind directions, for example, when do these directions appear, reappear, or change over time? So that's what Anya focused on. But what I, for example, can say is simply the statistics of how many of which size of fans we have, you know, that you cannot answer if you just look at the image. Yeah, there's a lot of smaller fans, but here we have a lot of larger fans. And if you don't go through everything, you don't know what's the relationship with that. So the really cool result is that you've at the end, maybe it was not so much a surprise, but more like the final understanding. That's the distribution of the sizes and the energies. So, for example, I can say that 90% of all the fans are below 100 meters. But then we have this 10% that are larger than 100 meters. And the interesting thing is that previous work that tried to simulate the gas dynamics of this and so on cannot explain the larger ones. Because these models were using simplified gas dynamics. So we tried to get funding for making it better. But yeah, these older works were trying the first direct, simple approach of modeling this all, and it cannot serve to explain all of these fans. So basically, we now have a quantitative statement that, yes, we understand 90% of the stuff, but 10% we still need to understand better. And Anya, I think some of your wind directions were a bit surprising, right? When appears what?
Actually, we had to change our own understanding several times about what's happening. And I think one maybe most obvious is that we still don't know when exactly the fans are erupting, because we have basically image once in a couple of weeks. And we see the changes. And we know from theoretical considerations that they correlated to the amount of sunlight that the area gets. And what we corrected definitely between the beginning of this project and now is that in the beginning we thought, oh, all of these fans erupt very early in the morning in early spring. You know, just sun comes up, and that's when everything happens. And I don't know, that was a little bit, again, naive and maybe even stupid from our side, because trying to correlate it with the wind, we noticed the common correlation in many areas, that it correlates to winds more like in the afternoon, lunchtime afternoon. And then we will coming back to the drawing board and thinking, but yeah, sure, we need some time to accumulate the pressure and to break. So the most of the solar radiation that's during the day is absorbed there will be around lunchtime. And then anytime after that, it should erupt, because that's when it's overburdens the ice. So that was one that we definitely shifted in our understanding, and it's again maybe not surprising if we would be smarter and thought about it beforehand, but we didn't.
Well,
that's
I
why you're
think we're
doing
still
this, right?
discussing. I just want to push back a little bit there, defending the Planet 4 results, because at some points, the modeling of the weather dynamics is also so complex that we could also say maybe there's a balance of where we are right and the modeling is wrong, right? So you have to be careful. It's just because, like Anya mentioned, the problem of all weather dynamics simulations on Mars is the lack of measurement points where you anchor the simulation to reality. If you don't have wind measurements, temperature measurements on a grid on the surface of Mars, all your simulations are free floating in math space, and you need to notch them to match reality. You just don't know where they really are. So, and that was a difficulty at the beginning, where maybe we always pushed back too much to the simulation until the simulator really made a good case for arguing, okay, there's the energy here and the winds are there, developing there. So yes, I also tend to believe now that they are erupting maybe more towards the afternoon than early morning. But I just want to point out that we need to do some modeling work of the jets and try to get funding for it. So any private citizens should talk to their senator to fund us. So that we can make more use, better, more precise use out of these data sets. Because if we would know when the jets precisely erupt, we would basically have a mini weather station on the Mars surface. Because we could then tell the simulator, I know the jet erupts at 4 o'clock, so you better tune your simulations so that that wind matches. As long as we don't know precisely when they erupt, we have this constant battle where maybe one party says we are correct or the other one says we are correct, right? So it's just the lack of knowledge.
And another part is that we didn't mention so far, but we never saw these jets in action. We only see the deposits that we mark, and big part of that is actually pointing the camera there at the right moment, because it's probably erupts, I don't know, minutes maximum, several minutes, because how
maybe
long
seconds.
do we, maybe seconds, how long do it take to empty a cavity like geysers do, right? So we really think that we never on the right time imaging. It connected to that most of the orbits of spacecraft are fixed on one time, so they always observe at the same time. But we're slowly starting to get those satellites that actually image at different times of days, like the Trace Gas Orbiter from Europe. They have also not completely free, but more variability in local time imaging. And Emirates mission also will have that, but they don't have a good camera.
They're also further away, but
yes.
Yeah, but the Trace Gas Orbiter was a good start, and this is the difference between polar orbit versus equatorial orbit. The equatorial orbit, if it flies around the equator with some oscillations, it sees just all the local times. And the polar orbit is always at the same local time, which is why from a polar orbit mission we wouldn't be able to scan different times of the day to check, did the jets erupt already or not? So that's not possible with a polar orbit.
But we also so far didn't have a good argument on, if we would know when exactly they erupt, we could try to convince people to shift the orbit or do something about it. But if we don't know, no argument to make.
Yeah, on top of that, there's a risk because we actually don't know if they are easily observable. It could be that the dust cloud that is nicely visible by cumulative deposition on the surface on a bright eyes, that's clearly dark. But while in air, it might be too thin. And that's another thing where we didn't have the funding for yet to do the simulation to calculate with radiative transfer, how well is a jet visible if it's currently erupting? And as long as we cannot persuade a whole mission that is really the case, they don't spend the fuel to change the orbit just for us. So.
Are you making these data sets available for other people to come and use for different projects, or you're not just hoarding all of this tons and tons and tons of data?
No.
It's freely available. It's basically attached to our paper for this first 2 years that we already analyzed, and we plan to continue doing that.
Well. Let me specify that even both kinds of data is available. And with both, I mean the end result of a catalog that gives you the location size parameters for both fans and blotches, but also the pre-stage of that, meaning the measurements of the citizens is also available. They are, of course, much, much larger files. But in case you want to redo my pipeline, if you feel so inclined, then you can do that.
Cool. Well, I think that we're just about out of time. We're a little bit over our hour. But Michael and Anya, thank you so much for joining us today and telling us all about your citizen science project, Planet 4. It was super interesting to hear all of these cool things that you learned along the way.
Always fun.
Thanks for having us. Was big fun. Yeah.
All right, y'all, that is our show for this week. Thank you so much for joining us. And we especially want to thank our guests, Dr. John Keller, Dr. Michael Aye, and Dr. Anya Portyankina. Special three-peat for you guys. Of course, these are always just excerpts of these interviews. So if you want to check out the full extended interview, you want to join us on our YouTube and SoundCloud channels. This podcast is also available on, again, YouTube, SoundCloud, but also Spotify and Apple Podcasts. You can also get to our latest episode from the Fiske website, www.colorado.edu/Fiske. And while you're there, you can check out schedules of the upcoming shows, guests, and topics, and submit any questions that you might have regarding these topics for our upcoming guests. We can pass those along and get your questions answered live and on the air. So be sure to throw some questions at us like that. You can also email them to us at fiskepodcast@colorado.edu. And be sure to like and comment and subscribe and do whatever you need to do to make sure that you do not miss another upcoming episode. And that's all we've got for you. So thank you again. We'll see you next week.